Hello, this is question 10 from paper 2 of May 2015, time zone 2. And it's a kind of a cool question. It's kind of a measurement question where you have to work out area, a bunch of different things, use your knowledge of graphing a little bit as well. We'll see how it goes. So the following diagram shows a square ABCD and a sector OAB of a circle center O, radius R. Part of the square is shaded and labeled R. So that diagram represents the words there. And I'm just noticing that it says here that angle AOB is some value theta, and theta has to be between 0.5 and pi. I can tell you now that bit comes in handy to know that later on, just FYI. Okay, so what I tend to do first of all, and it's a bit useless in a way, but I like to do it, and that is just to draw a diagram, even though it's right there already and I can just draw on the paper. I don't know, the actual construction of the diagram it's really rough, as you can see, but it kind of gives me a sense of what's going on. It allows me to draw inferences like, okay, so I'm told in the diagram that's theta. That's okay. I know that's R. Oh, and I know that's R as well because they are radiuses of the circle. So it just allows me to think about the problem, just the construction as I go along. A, B, C, D. Someone else asked me in class once, does it matter which way we order things, or is there some sort of convention? And I have to say, although the starting point isn't necessarily the same, like A could be there or there, but we tend to go anti-clockwise around the shape. So staying there, that'd be A, B, C, D, because it effectively gives us a left to right kind of orientation to our diagram kind of thing. That's just an aside. Oh, okay. And I have to show that the area of the square is equal to, well, I haven't shown you that. So the area of the square as part A is 2r squared 1 minus cos theta. And the first thing might be, oh my goodness, how the heck do I do that kind of thing? It's got r's in it and a cos theta in it, and that might start to give you a bit of a hint as to where to go. But I go back to my drawing and I consider it a little bit more, and I think, well, what would the area of the square be? Well, the area is length times length. And so my natural inclination, I'll do it in a different color just so it points out, is to label one of those sides as x, and then I can infer from that that the area is equal to x squared. So that makes me realize that what I need to do is work out what that area, what that side length is. So what? What have I got? I've got an area, a side length x here. I don't have any particular circle formula that works out the chord length, but I'm hoping you might notice that there is another shape in here other than a square and a sector. Give you a moment to think about that. Pause the video if you want to think about it further. But the shape that's also there is a triangle. And what I note is that I have in fact got enough information to work out what x is in terms of r and theta. And the reason why I'm comfortable with you leaving it in r and theta is because when I have a look at my my question, show that the area of the square is 2r squared 1 minus cos theta, the area is given in terms of r and theta. So I don't have to work out what r and theta is at this point. So that's good to know. So what do I have? I really have a limited set of things I can utilize to do with triangles. I've got sine rule, which is side over sine angle equals side over opposite side angle. That doesn't really help me. And the thing I was expected to show had cos in it. That's a bit of a giveaway too. It's not right angled, so I can't use right angle trig. But there is, of course, the cosine rule. And that's on your formula sheet. But the cosine rule basically says the square of one side is equal to the square of the other side plus the square of the third side minus 2 times that side times the cos of the angle between them. So let's put that together. We've got, I'll write the formula down just so you've got it. It's basically c squared equals a squared plus b squared minus 2ab cos c. So you can see that there's a relationship that between the side that you're looking for, it's the opposite angle, hence the little c and the big C, and A and B are just the other two sides of the triangle. So let's substitute what we know from the diagram. And we have x squared is equal to a squared. Well, A is just one of the other sides, that's R. And B is the other side, that's also R. Minus 2 multiplied by R, multiplied by R, multiplied by cos. And what is C? Theta. So if I simplify that, I get 2r squared, that's r squared plus r squared, minus 2r squared cos theta. Please, please, please remember that you can't subtract those two r squareds from each other because there is a multiplication between these two things, and that has to take precedence over subtraction. So you can't take them away, nor do you want to, because it won't get you the answer that you've been asked to find anyway. There's a common factor of 2r squared there. 2r squared times what will give you 2r squared? It's not times nothing, because 2r squared times nothing is nothing. 2r squared times 1 is 2r squared. And then I'm left with a cos theta in my second term. And that is the area, 2r squared 1 minus cos theta. So that's basically part A done. It's always nice when they give you a result to work towards, because at least it gives you a sense of where to go. Now, this bit here is a little bit confuzzling at first. When theta equals alpha, so what they're trying to say is that this representation could be for any angle between 0.5 and pi. Now let's take theta to be a specific angle. And I know it's just another variable, but that's kind of what it's kind of making it a constant called alpha. And saying when it does equal this value alpha, the area of the square ABCD, okay, cool, we know what that is. We've got an expression for it, is equal to the area of the sector OAB. Okay, that's fine as well, because I have a formula for the area of a sector. So I think I'm okay with this. I just need to translate this into an equation, because it says write down the area of the sector when theta equals alpha. Okay, I can do that. And then I need to find the value of alpha. And that's the tricky bit, but it just uses a GDC technique that you need to remember to use as often as you can get away with it. So let's go with part B here, 1, which was find the area of the sector. Well, the area of the sector, and I tend to like to use little subscripts there so I can keep track of what I'm doing, is equal to, well, if you look at your formula sheet, you'll find that if the angle at the center is theta, then the area of sector is half r squared theta, as long as theta is in radians. But I'm told that theta is equal to alpha, so I'm going to go straight to a half r squared alpha. Okay, and I'm told in the question that this area is the same as the area of the square. So I can straight away set that equal to 2r squared 1 minus cos, not theta, but 1 minus cos alpha. Okay, so all I've really done is I've substituted alpha for theta. Alrighty, let me take this down here where I've got a bit more room. And what I'm going to do is I'm just going to do a little bit of tidying up to make it a little bit nicer. So I'm going to multiply both sides by 2, because on the left-hand side, that'll just give me r squared alpha. On the right-hand side, I'll have 2 times 2, which is 4 r squared 1 minus cos alpha. Now, we've got an r squared on both sides, so I can divide the r squared out. And the reason why I can do that is because r is not equal to 0. Really good practice. It's not going to be required to do it in the exam. but it's a really good practice to write that down so we get a sense of where we're coming from. Oops, not theta, sorry, that's bad practice, isn't it? R does not equal 0. The radius has to have some length. So that's cool. We've now got an equation with just one unknown. But I'll tell you now, we don't have any tools at our disposal to solve this easily, even though it looks like a nice tidy operation. I can't divide by alpha because alpha is inside the cosine function and so on. But it ends up being a fairly easy task. What I'm going to do is I'm going to subtract theta from both sides, and I get 4 outside of 1 minus cos alpha minus alpha. Now that I've got an equation set equal to 0, I can use my GDC to solve. And this is such a powerful technique, it's worth remembering. When you've got an equation with one unknown, I rearrange the equation so it's set equal to 0, and then do the following. Off we go to this. Oops, that's the problem that I was working on before, so I'll get rid of that and start a new one. And this time I'm going to add a graph, not a calculator. And what I put into my graph is the function that I've got here, in this case on the right. It's the bit that's set, whatever set equal to 0. 4 outside of 1 minus cos alpha minus alpha. So I go 4 outside of 1 minus, where do I find the alpha key? Answer, you don't use it. You use the x variable because this is a function with respect to x. So you've got to do that translation in your head. So 4 outside of 1 minus cos x minus alpha, and alpha is x, so 1 minus x. Return. Look at that cool graph. So what do we do now? Well, this is where, as I was saying to you before, keeping a sense of what the problem is all about gives you a bit of a hand up in making sense of it, because it says that theta can go between 0.5 and pi. So what I'm going to do is I'm going to zoom this part of the graph down to that little part. So I'm going to go to Menu, Window Zoom, and not just do a zoom in and out kind of thing. I'm going to use my window settings, and I'm going to say, well, I'm going to go a little bit before 0.5. So I'll just go to 0, and I'll go a little bit above pi. Pi is what, 3? You can actually just type in pi, by the way, and then it will go to pi. But I'm actually just going to say, well, I know that pi is 3.1 something, so I'm going to go to 3.5. And I don't care about the y value so much at the moment. I'm interested in the x value, so I'm just going to click on OK for that. And now I've got my graph showing really nicely the bit that I'm interested in, like so. Okay, now why is this important? Well, this is the function which shows all possible values of x and the corresponding y values. But what we're interested in, is if this is the function setting y equal to 0. So where is y equal to 0? Here, but that's below 0.5, and here. So if I can work out where it crosses the x-axis, I've got the value of x, which will be alpha, when y equals 0. So I go to my menu, I go to Analyze Graph, and I select 0. I go anywhere to the left of that 0, anywhere to the right of that 0, and it'll punch out 0.511. So that's the value I'm looking for. When y equals 0, x equals 0.511. So I can say, therefore, by the GDC graph, alpha equals 0.511. Sometimes I will draw a graph if I think it might be useful, particularly to make sure that the marker knows what I'm doing. So I might go like that kind of thing. And that might just give the marker a better sense that I know what I'm talking about and how I did it. If you're running out of time, maybe don't do it, but there we go. Okay, so that's 1 and 2 done. Sorry, that's 1. And here is 2. Last one is worth 8 marks. It's not as bad as it looks in terms of getting it right, but what makes it tricky is that there's a few parts to it, and you have to know what you're doing, I suppose. So I like to start with making sense of it. When theta equals beta, that's what that funny old B looks like. When theta equals beta, the area of R, okay, so that's that shape there, is more than twice the area of the sector. Okay, it's more than twice the area of the sector. Find all possible values of beta. So there must be multiple values that will work. Okay, so what am I looking at here? I'm saying for some values of beta, oops, R is bigger than the area, twice the area of the sector. So I'm just writing it down algebraically because it helps give me some sort of sense of what I need to do. Well, I know the area of the sector. The area of the sector is just a half r squared beta. So that's okay. So twice the area of the sector is equal to twice a half r squared beta, which is just r squared beta. Okay, that's cool. So I need to work out the area of the region. So the values of beta such that the region is bigger than r squared beta. All right, well, that's something. I obviously need to work out what r is. So when I look at the picture, and here it is here, I can see that this is r here. It's r is going to be the area of the square minus the area of this thing here, which is a segment. There's no formula that we know that's the area of a segment. Whew. Well, what am I going to do? Well, to work out the area of the segment, I'm going to, well, I've got an area here that I know. That's the area of the sector. And then if I take away the triangle, then I'll get the segment. Okay. So I'm going to start off with working out the area of the segment. The area of the segment is equal to the area of the sector minus the area of the triangle. Okay, well, the area of the sector, that's easy enough to do. The area of the sector is a half r squared beta. So that's okay. What about the area of the triangle? Again, pause the video if you want to just think about it. So here's the triangle here. And what I might do, I think, to help myself out, I think, yeah, I think I will. What I might do is just pull out the triangle. So I often do this with diagrams. I've got R, I've got R, I've got beta now. And I've got whatever that side length there is. So I've got this. Okay, so to work out the area of a triangle, I need to use one of my formulas. I've really only got two. I've got half AB, sorry, a half base times height, and I don't have the height of this triangle because it needs to be from the corner to the perpendicular height from one of the vertices to the opposite side. Don't have that, but there is that other formula which is on your formula sheet, and that is that the area of a triangle is a half AB sine C. Half AB and the sine of the angle in between. Now again, this is a bit of a winner for me because it's going to be in terms of R and beta. So let's do that. Area of a triangle is a half R times R, which is R squared, sine beta. So therefore, the area of the segment is equal to a half R squared beta minus a half R squared sine beta. That's all right. Okay, what next? Well, the reason why I did that is because I know that R, which is the area of that region, is going to be the area of the square minus the area of the segment. And the good news is that we've been given the area of the square in part A, if you remember. So let's put it all together. I'll have to do it on the next page, unfortunately, so I might just need to do a bit of flicking. So the area of the square was 2R squared, 1 minus cos theta, but in this case, theta is beta, so 1 minus cos beta, minus the area of the segment, which was half R squared beta minus a half R squared sine beta. Okay, so half R squared beta minus a half R squared sine beta. Okay, and again, because I've got subtractions there, I'm keeping that minus to make sure that I don't stuff up. So that gives me 2R squared, 1 minus cos beta, minus a half R squared beta, plus a half R squared sine beta. Okay, let's put it all together. That's what R is. So remember from the other page that we started, well, we did some working out, and we had R is greater than R squared beta. So now I need to substitute this whole big expression for R, and I get therefore 2R squared, 1 minus cos beta, minus a half R squared beta, plus a half R squared sine beta, must be greater than R squared beta. Okay? Now, I can keep an inequality happening as long as I'm only adding and subtracting. So I'm going to subtract R squared beta from both sides. Now, there's an R squared beta term here. It's a half R squared, which I'm just going to treat as 0.5. So I've got 0.5 R squared beta, and I'm subtracting an R squared beta. So I've got 2R squared, 1 minus cos beta, minus 1.5 R squared beta, plus 0.5 or a half R squared sine beta is greater than 0. I wonder why I'm doing this. Can you think of why? Give you a moment to pause and think. I'm doing all of this because I'm going to utilize the same technique as I did in part B. If I can get an equation equal to 0, or in this case greater than 0 for an inequation, then that I can graph, then I can utilize that to work out the value of beta. Okay, so the problem with this equation is that there's an R squared or an R variable as well as a beta variable. But the good news is R squared, and R squared. Okay, so I'm going to divide through by R squared, and I get 2 outside of 1 minus cos beta, minus 1.5 beta plus, I'll just go to 0.5, sine beta is greater than 0. Now, the reason why I can do this is a little bit more fancy than just saying r is greater than 0. R is not equal to 0. I actually need to say that r squared is greater than 0. Basically, the reason why is that if this value here that I'm dividing through were negative, then when I've divided through by it, it actually changes the inequality the other way. So r squared greater than 0 is kind of important. Of course, any value that you square will be greater than 0. Truth is that r has to be greater than 0, doesn't it? Doesn't because a radius can't be negative. Okay, now here's the bit that you need to appreciate from this point on. This looks complicated, but it's easy to graph. Note this is important. This is that so if this is going to be our function, we want to work out values of beta such that the function is greater than 0. So let's go to our GDC and see what that means. I'm going to select that graph and delete it. I can just click on this one and delete it. And then I'm going to go Control G to bring up my graph again. I'm going to type in that graph, but again, substituting x for beta. So 2 outside of 1 minus cos x minus 1.5x plus 0.5x, sine x, sorry. And that gives me a funny old graph here. And you can see that's quite squished, which I don't like. It's a bit unclear. So I'm going to go to my menu, go to my Windows Zoom, go to my Windows settings, and I'm going to leave this because that's kind of good to have. But I'm going to change the y minimum to, I don't know, -1 and 1 by the looks of it. Yeah, that looks reasonable. If my graph went off the page, then I'd go back and do something else. So that's fine. Now, remember what the name of the game here is. We need to work out values of beta such that this bit here, 2 outside of 1 minus cos beta minus 1.5 beta plus 0.5 sine beta is greater than 0. If that bit there is greater than 0, then it's appropriate values for beta. Looking at my graph, if this line represents, if above and below represents positive values and negative values of y, then this is positive above the x-axis. So in other words, if I can work out the zeros here and here, then what I have is everything in between are appropriate values for beta. So I go to menu, I go to analyze, I go to 0, click to the left and to the right of 1. There it is there. Menu, analyze, 0, click to the left and right on the other side, and I've got another one. And you can see at 1.31, this thing here equals 0. At 2.67, this thing here equals 0. So I've got 1.31 and 2.67. Okay, so if I go back to my my graph now, and I'll just finalize on slide 6 then. So again, it wouldn't hurt for you to draw a quick graph, a quick sketch. If you have stuffed something up, it sort of tells, oops, that's probably a bad one. I'll do that again. Quick sketch, and sort of went down, then up, and then down, like so. This bit here was 1.31. That's the lower boundary for beta. This bit here is 2.67. That's the upper boundary for beta. You can even, if you want to, sort of, if you've got a different color, you could sort of hash the bit which is appropriate, and you can conclude, i.e. beta, oops, that's badly done, i.e. beta is between, we use our less than and greater than signs like that to squish in beta, 1.31 and 2.67. And that's the correct answer. Note, it's not less than or equal to, because we're told the region is greater than. If we were told the region is greater than or equal to, then we would include those points. But because we don't include those points, it's we just use the less than and greater than symbols. And that's it. Again, you can see on the mark scheme, question 10, show that the area is like this, work your way through using the cosine rule to show that, so that's fine. Note, award no marks only if the only working out is 2r squared minus 2r squared theta. So, you do have to do some work. Part B, a half alpha r squared is all it was looking for. Part 2 was to set them equal to each other, down to 0.5111, and there was our 0.5111 there. Part C, attempt to find R, subtraction of area, square minus segment, correct expression for the segment area. And you know what? I broke it down a lot more because I wanted to unpack the thinking behind it. How do I find the segment area? The segment area is going to be the sector area minus the triangle area. Correct expression for R, there it is there. Correct inequality, there it is there that we did. Correct inequality in terms of angle only, although I subtracted beta from both sides to get mine. Same difference though, same deal. The important thing is correct inequality in terms of angle only, i.e. we've got rid of the r squared. Attempt to solve their inequality, in this case, e.g. sketch or one correct value. So there's a method mark there. And then both correct values have been found, and correct inequality 1.31 and 2.67. And we've got, here 1.31 and 2.67. So to finish this video off, I'll just stop by saying that I guess if there's one thing you can take away from this problem is, number one, complex problems can always be made less complex by breaking them down into simpler ones that you can solve. And if you look at that mark scheme, you can see that you do receive marks for steps along the way. Number two, using the graph of an equation with an unknown and finding zeros or points of intersection or something else is frequently an excellent way to solve an equation using your GDC.